All right, today's lesson is lesson 2.5, similar figures. The key idea is that figures that have the same shape but not necessarily the same size are called similar. When two figures are similar, we know that the corresponding side lengths are proportional and that the corresponding angles are congruent. So these are two very important points right here. Okay. When we talk about corresponding side lengths, we're talking about the sides that are in the same position, relative position, so A to B and D to E. So when you write a ratio, AB over DE, it would compare to the other corresponding sides, like the blue sides here, BC to EF, or green, AC to DF. So identifying similar figures. So in example 1, they want to know which triangle is similar rectangle is similar to rectangle A, and so each figure is a rectangle, so corresponding angles are congruent. Check to see if the corresponding side lengths are proportional. So they have done that for you right here. Rectangle A and B, when they're looking at those two, they're looking at the length of A to the length of B because those two sides correspond, and they're both in blue. So 6 over 6 would be equal to 1. How do the widths compare? 3 over 2, which is the width of A to the width of B, but 3 over 2 does not equal 1, so therefore they are not proportional. When you compare rectangle A to rectangle C, the length of A to the length of C is 6 over 4, or simplified, 3 over 2, and the width of A to the width of C is also 3 over 2. Since those are equivalent ratios, rectangle C is similar to rectangle A. Right? What if we draw a new rectangle? Okay, rectangle D has units that are 3 and 1. So the length is 3 and the width is 1. And this is rectangle D. Okay, so if we're going to compare, let's say we'll compare D to A. We would take the length of D, which is 3, over the length of A, which is 6, and we would see if it is equal to the width of D, which is 1, to the width of A. Since 3 over 6 simplifies to 1/2, and that is not equal to 1/3, then rectangle A is not similar to D. Let's try D to B. So we'll take the length of D over the length of B, and we'll check to see if it is equivalent to the width of D over the width of B. Since 3 over 6 simplifies to 1/2, and it is equal to 1/2, those corresponding side lengths are proportional because they reduce or they are equal to the same ratio. Rectangle B is similar. And we could go through the motions for rectangle C, right? We could look and see if 3 over 4 is equal to 1 over 2. And we know that 3/4 is not equal to that. And it doesn't make sense because we knew from the previous example that rectangle A was similar to rectangle C. So therefore it would not be similar to rectangle D. So the correct answer is rectangle B. In example 2, we're finding an unknown measure. So we're going to use what we know about these corresponding ratios. And so they're setting it up because the triangles are similar, corresponding side lengths are proportional, and we're going to write a proportion. So we're going to take the shortest side from the small triangle, 6, and compare it to the shorter side from the large. So 6 to 9 would be equal to, get the other side from the small triangle, 8, and the corresponding side from the large triangle, x, to write this proportion. Remember that cross products in proportions are equal. So you have an equation, 6 times x is equal to 9 times 8, or 72. Divide both sides by 6 to find that x is 12 meters. So let's apply this in the next two examples. We could take corresponding sides to find this out. So we could take the slanted side from the small and compare it to the slanted side from the large. So we could take 6 over 9. Now make sure that your second ratio compares the same thing. So we have to go back to the small to get the other side of x and compare it to the other side of the large. Cross products are equal, so we have an equation. 9x is equal to 36. When I divide both sides by 9, I get x is equal to 4 feet. Again, don't forget the unit label if one is given. For number 3, I could also compare things in any way. So I could take the large to the small. So I could take the slanted side of 14 over 7, as long as I'm comparing it in the same way. Now I'm going to take this longer bottom side to 12, so x over 12. So in this case, I have 7x is equal to, and when I multiply these, I get 168. So when I divide both sides by 7, I'm going to get x is equal to 24 centimeters. All right, you may have set it up differently, but you should always, no matter how you set it up, result in this cross product equation. So there's lots of different ways we can talk about setting it up and thinking proportionately. The important thing is that when you decide on your first ratio, no matter what it is, your second ratio has to be set up the exact same way, okay? So it has to be comparing the same things across the equal sign. Okay, and in the last example, we're talking about a real-life application about a painting and a replica. So they've given you the dimensions off to the right and they show it to you. So basically we want to know what is the height of the replica, and so we'll take the corresponding sides. We'll take 3.75 over 15 would be equal to h over 12 and find that the replica height is 3 inches. So that for our application, when we try it, what if the dimensions now are saying we just found that this height was 3 inches, but what if the side of the replica was 4.5 inches? What would the actual longer base of the painting be right here? So we could set this up again however you want to. You can take 12 over 3, right, would be one way. All right, so if I'm taking the short side of the painting to the short side of the replica, then I have to take painting x over the other side that we know. Okay, so when I cross multiply, I'll get 3x is equal to 54, and when I divide both sides by 3, I'll get x is equal to 18 inches. And don't forget your unit label.